To prove that Euler's characteristic theorem holds for all convex polyhedrons, not just the regular polyhedrons that we've looked at in class, we're going to use the result of the last video, the fact that all planar graphs do satisfy the characteristic equation. First of all, though, let's see what a convex polyhedron is. The best way for me to show you probably is to draw one that isn't convex. So let's see if I can do that. Let's just draw like a staircase here with 2 stairs. Okay, so you see here's a staircase, and it's definitely a polyhedron. All of its sides are polygons, and if I take 2 points, I can easily find 2 points on this polyhedron where the line segment that joins them is not completely contained inside the polyhedron. That means it's not convex. A convex polyhedron is one where you pick any 2 points on it and connect them with a line segment. That line segment stays on the inside of the polyhedron, like soccer balls and all of the regular polyhedrons that you've looked at. To convince you that this is true, we're going to look at a hexahedron. It has 6 faces. And I think when you just look at this one example, you'll see that that our statement is true for all convex polyhedrons. To prove the characteristic holds for those, we must use the fact that every convex polyhedron corresponds to a planar graph that has exactly the same number of faces, edges, and vertices. Now, why will this be all we need to do? Well, the reason is because you know that every planar graph satisfies Euler's characteristic. So if we know that there is a corresponding planar graph to each convex polyhedron with the same number of faces, edges, and vertices, then we're done. We know that the characteristic will hold for all of them. So just take a quick look at this hexahedron here. It has 6 faces. Notice it's not regular. If I look at this vertex, I see 3 edges coming into it, whereas 4 edges are coming into this vertex. So it's not regular, but it is a convex polyhedron. We're going to imagine that this hexahedron is made out of a very soft rubber, and we can poke a little hole in it and blow it up to look like a sphere. And if we did so, we would still, of course, have the same number of vertices, edges, and faces. It's just it has the shape of a sphere rather than as a polyhedron. You can imagine blowing that up, I hope, and it would look like on the right-hand side. But let's do a little more here. Let me label these vertices. This would be 1, 2, 3, 4, and 5, and they correspond over here, 1, 2, 3, 4, and 5. And let's get these edges corresponding. The faces. Let's call this face A, and this face B, and the face in the back C, and down here the face, we'll call this face D, and this face E, and the one in the back F. So I do that so that we can go over here and see the corresponding regions on the sphere. Let's see, A is it goes from the edges of A go 1, 2, 3. So 1, 2, 3. So this is A back here. This one in the front is 1, 3, 4. So 1, 3, 4 is B. And this one is C. Down here, let's see, from 2 to 3 to 5. 2, 3, 5. That's D here. And this front face that we're looking at is 3, 4, 5. And 3, 4, 5 is E. And this will be F. So the hexahedron is pretty easy to do with this with. That's why I chose it. You can get much more complicated looking drawings, but hopefully you can see that any convex polyhedron could be blown into a sphere and you have exactly the same regions. It's just that the edges don't look like straight lines anymore because they're on a sphere, and the regions don't look like triangles because they're on a sphere. Now imagine doing this. Imagine taking our face E. That was the one in front here. In fact, I really should label these for you. This was D, this face was E, and this face was F, and over here this was A, and this front face was B, and this was C. So we should have those labeled. Now imagine taking this balloon and cutting a hole in one of the faces and spreading that hole open and spreading and stretching and spreading until it laid flat, until it became a plane, and the drawing on the balloon would become a planar graph. Let's see how that would happen here. Let's take our hole in face E. So we're going to cut a hole in E, like right here, pop a little hole, and then take that hole and spread and spread and spread until it's flat. Now, the edge E, the hole that you cut, becomes the edge of the plane, doesn't it? The hole that you cut becomes the edge of the plane because you've spread it all out. Now I found this to be kind of hard to figure out to draw this picture, and there'd be other ways you could draw it, but this is one way that works. How would the planar graph look like when you did this after you spread it all out? Well, E would be the outside region, because E, you spread out, this yellow is the hole actually that has spread out to be the edge of the plane. Now we just have to, I carefully looked at it and I saw that 3, 4, and 5 are on E, right? Look, over here, 3 to 4 to 5 are face E. So I have to have 3, 4, 5 on the outside, and these are those edges. And then I figured out how the others had to go. 3 had to connect to 1, and 1 to 4, etc. By looking over at the sphere, I got this. Now let's label the faces. The face from 1 to 3 to 4, 1, 3, 4. So this is B. And 1, 2, 4. 1, 2, 4 was C. And 3, 1, 2, 3, 1, 2 was A, and 3, 2, 5, 3, 2, 5 was D, and 2, 5, 4 was F, and again E, because that's where we punctured the hole and stretched from. E is the outside. Now if you look back to our original hexahedron, you will see that the vertices were 6, the edges were 9, and the faces on the hexahedron, there were 6. Notice that V plus F is 12. Whoops, I had to miscount. I miscounted there. Sorry about that. I'm not going to go do the whole thing over. The vertices were 5. Go back and look at the hexahedron. You'll see vertices were 5, edges were 9, faces were 6, and so V plus F is 11 minus 9 is 2. Well, let's choose a different color here. I'll choose yellow, and let's see what it is for our planar graph that corresponds to the hexahedron. We see that we have still 1, 2, 3, 4, 5. Vertices is 5. edges 1, 2, 3, 4, 5, 6, 7, 8, 9. Edges is 9. And the faces 1, 2, 3, 4, 5, 6. Faces is 6. So you see that it is exactly the same. Every convex polyhedron can be blown up onto a sphere, popped in one face, spread out on a plane, and what do you have? You have a planar graph with exactly the same number edges, faces, and vertices that you had on the original convex polyhedron. So now that we know that, we know that all convex polyhedrons do satisfy Euler's characteristic formula.